Hey guys, all right, today we're going to talk about chemistry of life. This is the second set of notes for water chemistry. Okay, so let's get started with that. Okay, so a couple things just about chemistry of life that are really important. We want to know what a chemical reaction is and what are the parts of one. We kind of talked about that in the last video, so that should be a refresher or a little bit of review. This PowerPoint, we're really going to talk about the characteristics of water that make it important. We're going to talk a little bit about acids and bases and a little bit about the pH scale, okay? Just enough to get us some information we need for biology, all right? So let's get going. First, water is absolutely essential for all life on Earth, okay? That's really important, okay? You probably already know that. Something that you might not know is about 2/3 of a cell's mass is water, right? So when you see commercials or something like that, so the human body is, 66% or whatever, 70% water, sometimes they round. What they're basing that on is the fact that a cell is about 2/3 water by mass, okay? And that water is actually found in the cytoplasm, right? Which we will learn about later in the year, okay? The jelly that kind of everything in the cell floats in. Now, the most important thing about water for biology, and I mean the most important thing for the whole year, water is polar, okay? And polar, that should make you kind of think about the globe. So actually, let's go with green here. If I have green, yeah, green. Okay, so here's the Earth, just like that. We know the Earth sits on a tilted axis, maybe not quite that tilted, but at the top we have the North Pole, and at the top we have the South Pole, okay? And so the term polar should make you think of opposites. And in fact, we're talking about opposite charges, okay? And, when you think of the Earth, right, I'll see if I can, let's make this pretty. Right? So that's a really rough South America, isn't it? I'm not by any stretch an artist. Let's see, here's Hawaii, we got Alaska. Alaska, there's Canada, and there's Greenland up there, right? There's Hawaii, Russia's coming over. Yeah, there we go. Got the North Pole. Yeah, okay. So that's a decent Earth, I guess. Let's see if we can color that in there so it looks like it's one big place. Hey, there we go. Okay, so we think about the polarity of the Earth. It has a North Pole and a South Pole. They're opposites, all right? When we think about water, all right, when we think about the charges on water, hopefully you've already watched the last lecture, right, the one on chemistry and atoms and that kind of thing. You will have noticed that I drew water like this. I put 2 electron pairs at the top of oxygen, hydrogen's down there. And you probably also remember I showed you that this sign means partial. It's a delta, okay, a lowercase delta, or sorry, maybe it's a sigma. I don't remember all my Greek letters. Regardless, it means partial. So this is a partial negative, and this is a partial positive, okay? And a lot of times we draw it like that, but it's easier if we draw this thing called a dipole arrow. It's called a dipole arrow. The prefix di means 2. Pole is talking about polar, all right? So 2 poles, arrow. It's positive down here where the plus is, and as you follow the arrow, it becomes negative, okay? And because water is polar, it can do all of this wild stuff, all right? And which makes it absolutely essential for life, okay? So let's look at some of those things. Number 1, water is the universal solvent. A solvent is something that dissolves stuff, okay? And water is a universal solvent because it is polar. The fact that it has a positive and a negative end means that when you put a salt, right, which is a metal and a non-metal, so that's from the last presentation. If I put Na, which is usually plus, and Cl, which is minus, and I put that around some water, well, water has a kind of positive end and a kind of negative end, and so negatives repel, but opposites attract. So the sodium will want to be close to this end, and the chlorine will want to be close to that end. It allows water to surround atoms and other molecules and dissolve them, to hide them in the whole solution, okay? So since the cytoplasm is mostly water, things can dissolve into the cell and move around the cell, which is really important. Okay. The second thing, water has a high heat absorption capacity, which means in order to get water to change from like a liquid to a gas, you have to give it a tremendous amount of energy. So this is how sweat works. Okay. When you sweat, you get water draw. So I'm going to draw like here's an arm. I'm just going to call this the arm, right? And it gets little beads of sweat on it. Okay. And heat, let's go with red. Heat from the arm, right, from your muscles, from the inside of your body, is being given off by the arm, and it goes into those sweat droplets. And as the water absorbs that heat from your body, eventually, okay, it will evaporate, right? Evaporate. Well, when it evaporates, it takes that heat energy with it. It removes it from your arm, okay, and that keeps your body from overheating, right? So it helps keep your temperature the same. This is an important part of homeostasis, right, which we've talked about before. Okay, so another thing that's, I guess, really important about that, as far as the high heat absorption, is it also keeps you warmer, right? So as the temperature outside cools down, the cytoplasm in your cells are holding a lot of heat. And so it takes time for that heat to be given off. It helps you keep your temperature warm if it gets cold outside. Something else that's really important, because water is polar. Solid water, right? So solid water is ice, okay, is less dense than liquid water. So ice floats. Now that's really, really, really important. It also makes sense, okay? This is water, okay? We have the red oxygens, the two white are the hydrogens. And these purple sticks, okay, are showing hydrogen bonds, which we talked about in the last video. And those hydrogen bonds go from the negative oxygen to the partially negative oxygen to the partially positive hydrogen. And you'll notice that it forms this shape, right? It's very organized, okay? And when water starts to freeze, it locks the shape in, and these empty spaces inside trap air. And so this buoyant is buoyant, right? It can float on water because it's got all this empty space in it. Most things, when they freeze, they get more dense. But if water was like that, then, you know, if we draw ourselves like a little lake here, we have a fish in the bottom. There's our couple fish. Okay, there we go. There's our water. Right. Well, when it gets cold out here and the top freezes, right, because the top's going to freeze before the bottom, well, this would sink and they would all die and they would be sad. Well, that doesn't happen, right? Because there's all those little holes, right? We look at it like this. We can kind of draw it out. Remember, our dashed lines are hydrogen bonds, right? So all this empty space gets filled with air, right? It's like a pocket, and there's nothing in there, right? There is something, there's air in there, but there's not water molecules in there, so it's less dense, right? So this is a hole or a pocket, okay, for air, and that keeps the ice floating and keeps all the fish from getting crushed. Plus, it actually acts as an insulating layer, and it keeps the rest of the water from getting too cold. Okay, now something else that's really cool from this, if you have like a glacier, right? Here's a big glacier, and we drill down into the glacier, we bring up an ice core, right? We can take that core and all of the air pockets in there, we can like take a needle, a special kind of syringe that's made to extract air. You put the needle in the ice, you pull out the air, and you can test and see what the air was like a long time ago, right? So if you're interested in paleoclimatology, which is the climate of the past, we often use ice cores in order to study that. So some really cool things there about water. Now, we said a minute ago that water is the universal solvent. So let's talk about what it means to be a solvent for just a second. A solvent is something that dissolves something else. The thing that gets dissolved is called the solute. So the solute gets dissolved, okay, and the solvent does the dissolving, okay. And the reason that water is called the universal solvent is pretty simple. It can dissolve pretty much anything. Pretty much anything with time. So some things take a long time for dissolve. Some things don't want to be dissolved by water, some non-polar things. But eventually water will dissolve everything at least a little bit. So it is called the universal solvent. Now, when you dissolve thing X into thing Y, right, you make a solution. And if the solution looks the same the whole way through, we say it's homogeneous. Okay, so remember, this prefix means the same, okay? And genius has to do with, I can remember how to spell it, throughout. So it looks the same throughout, okay? So some examples of a solution, right, would be like sweet tea. So sweet tea is definitely homogeneous. It's just a brown liquid the whole way through, but we know it's water that has dissolved tea leaves and sugar into that solution, but you can't see like, oh, there's a spot where there's a whole bunch of tea leaves, right? Another example of a solution would be, let's see, sugar water, right? That you feed a hummingbird, but that's kind of the same sweet tea. Say coffee. Coffee is a solution. Coffee is a great solution. And you've probably seen a t-shirt that says alcohol is a solution. Well, in chemistry, yeah, in biology, alcohol is actually a solution because it looks the same throughout. So basically, you know, Coke would be a solution, right? Sprite would be a solution. It's stuff dissolved in water. Air is a solution because air is a bunch of things dissolved together and they look the same throughout. So remember, it doesn't have to be dissolved in water. Okay, it's just a mixture where things are evenly spread out. Okay, there's one substance dissolved into another. Now, when we say dissolve, that actually has some scientific connotations that go with it. It actually means something. So if you take chemistry, then we'll actually learn about this a whole lot with great detail. We'll learn about hydration shells and how water splits things apart. But in biology, we just want to look at the basics, right? We want to introduce you to the idea. So to dissolve something really means to split it into its parts, and if it's a salt, and hide it amongst the water molecules. If it's not a salt, instead of splitting it, we just completely hide the whole molecule. Okay, so with salt, all right, out of water, you put it. You know, you look at it. We have Na, and we have. Pick a different color here, Cl, right? And it's bonded together. When you put it into water, right, I have Na plus and I have Cl minus, and it has a charge. And what water does is the water molecules surround it, all right? So the hydrogens are going to be close to the Cl because the hydrogens are those partial positives, okay? And in chemistry, we'll talk about how this happens. If you end up to AP chemistry one day, we'll talk about it as it regards to thermodynamics, which is pretty interesting. But then around the sodium, the oxygen is going to be pointed towards the sodium because remember the oxygen is kind of negative. Okay, and so since it surrounds it all the way, we have hidden those ions in solution. So we've dissolved it, right? Acids and bases work this way too. Acids are chemicals that have protons, H plus, so a hydrogen ion is a proton, and they can donate those to, you know, chemical reactions. So anything that can donate a hydrogen is called an acid. Anything that can donate a hydroxide, which is an OH minus, is called a base. So a common acid that you've probably seen is hydrochloric acid. Remember, anything that starts with an H is going to be an acid, all right? When you put this into water, you get H plus and Cl minus, the leftover in this case. If you did the acid we talked about in the other slide, so H2SO4, which is sulfuric acid, you get HSO4 minus left over because you have an H plus, right? So you've removed one of the hydrogens, all right? For a base, a common base is NaOH, right, which is lye. Okay, we use it to make soap. It's pretty interesting stuff. When a base goes into water, the OH comes off and you get the leftover, which in this case would be a sodium ion, right? So there's my OH, and there's my sodium. So both of those things dissolve well in water. Something that's worth knowing, acids and bases dissolve well in water, and that's what they do, okay? Now, since we're talking about acids and bases, let's talk about pH for just a minute. The pH scale tells you how much hydrogen ions, the H plus, there are in solution. So when we're talking about the quantity of something in solution, we call that concentration. So this is quantity in solution. And the greater the quantity, the stronger the concentration. So if you have a pH of like 1 or 0 or 2, something like that, you have a lot of hydrogen ions in your solution. If you have a pH of 14, you don't have any, right? You have very little. But you would have a lot of OH in solution. Now, there is another scale. It's called the pOH scale, and it's just backwards. It would say little OH minus, lots of OH minus. This would be the pOH scale. Now, you don't have to worry about the pOH scale. We just talk about pH in biology, but it is worth knowing that it is there. So remember that acids are like 0, 1, 2, 3 on your pH scale, 4, 5, and 6 getting close to neutral, 8, 9, and 10 still pretty close to neutral, but they are definitely basics or bases, right? They'll be on the basic side of the pH scale. And then, 14, 13, 12, 11, those are going to be your pretty strong bases. Lye, when we talked about a minute ago, actually has a pH of 14. Hydrochloric acid, which is in your stomach, actually has a pH down between 0 and 1. Okay, so interesting stuff. If you put an acid and a base together, they actually neutralize. Okay, and something that's pretty cool to think about is acids have H plus, bases have OH minus. When you put those together, you get water. So anytime you put an acid and a base together, they neutralize. They make water, and they also make a salt. Remember, a salt is a metal and a non-metal. And this is one of my absolute favorite things about biology and chemistry. So if you take HCl, which is a very strong acid, and NaOH, which is a very strong base, this H right here, okay, this H and this OH come together to make H2O, to make water. And the salt is this metal and this non-metal, which is NaCl, which is table salt in this case. It's not always table salt, but in this case it is. So pH of like between 0 and 1, pH of 14, you make salt water when you put them together, which is just cool. That's interesting, okay? We'll talk more about neutralization reactions in chemistry, okay? But just to have a foundation for biology is a good thing to start. So now we should, again, know the chemical reaction. Okay, it's the thing with the arrow, shows bonds breaking. Reactants on the back of the arrow, the products on what the arrow point to. The big thing from this, okay, we want to know the characteristics of water that are important. And the number one big one is the fact that it's polar, okay? Remember that your acids have hydrogens out front. Your bases have OH minuses at the end that they want to give off, okay? And we want to be able to identify the pH scale, which goes from 0 to 14, okay? So those are the notes for water and pH, okay? So if you have questions, shoot me an email, let me know, and I'll be glad to help you with any of those, all right? So see you guys on the next video.